of this webinar is essentially to describe the new features and capabilities of our software, which is new release of ASAP, Atomistic Simulations Advanced Platform. It was a new release in the beginning of this year. We call it version 23.0. And we will be talking today about general presentation, what is Simune. We show how ASAP is working, and the new feature, which is nano-Transport for calculations with our software. So let's go to the next slide. A couple of words about the company. The name of the company is Simune. We are located in Spain, North Spain, in the Basque Country, in the beautiful city of San Sebastian. So you can see on the map, and the beautiful view, which is taken from Wikipedia, and the yellow dot is showing where is our offices. So San Sebastian, a part of the beautiful city, it's also a center of a strong research scientific community. We have several research centers and the national state university. So we have a great background for the scientific development. Let's go to the next slide. Right. So Simune is the company which is developing software, but on the top of that, we also provide scientific consultancy services. So we provide consultancy for industries in the field of material simulations. We provide analysis of the properties. We do scanning of the materials. We provide knowledge and overview of the chemical reactions, processes happening in new materials and existing materials as well. So on our website, which is given, the link is given at the bottom, we have a number of case studies which you can check and see what exactly we can simulate and what kind of properties we can study. Let's go to the next slide. Right, let's go to the topic of this today's webinar is about Atomistic Simulation Advanced Platform, so ASAP in the contraction. So this is the graphical user interface, which is supplied ready to use. It doesn't require any installation. This software is supporting different platforms. It works on various flavors of Linux, Macintosh, and Windows. As a DFT solver, ASAP uses Siesta to calculate material properties. The view of the interface of ASAP is given on the picture. So essentially it consists of the panel, and you see the projects with different status. We will describe it later. So the standard workflow working in ASAP looks like following. So there is a diagram on the bottom. We start the system definition, then we define the project type, and then we choose the calculator. In that case, it will be Siesta, for example. Then we run our simulation locally or remotely. And finally, ASAP analyzes the results and visualizing them in the widget, so we can see it on the screen. Let's go to the next slide. So let's focus on the workflows. So ASAP allows a very flexible and powerful definition of the system using structure builder. So from the panel on the top, you can choose a structure from the existing library. It can be molecule. There is a big library of different molecular structures. You can construct custom cut surface, slab. You can use bulk construction for different symmetries. There are nanotube and nanocluster constructors. On the top of that, a user can load pre-existing system in lots of various structure formats, including XYZ or C for cell or Siesta, and load into the ASAP. Let's go to the next slide. As soon as the system is defined, we can choose to run a different project. It can be single point calculations just to check the energy, or it can be geometry optimization to find the lowest energy, or it can be molecular dynamics with different algorithms. It can be with ASI or with Siesta. And then there are a bunch of different projects written on the bottom. So, for example, here we choose geometry optimization, and this opens a new window which allows to customize what kind of properties we would like to calculate and how we're going to run. Let's go to the next slide. So there are various project types in ASAP. So single point calculations, it's the simplest project. This essentially calculates the ground state of the system, convergent electronic subsystem of the system. So the outcome of this project is electronic structure, for example, density of states, local density of states, PDOs, etc. It brings total energy of the system, HOMO-LUMO energies of the system, Fermi energy. The outcome of this project also includes charge analysis. The project can be applied to molecules, surfaces, and bulk, and any system you defined in ASAP. Next project is molecular dynamics, which is essentially evolution of the system under given conditions, essentially pressure, thermostat, temperature, time, step, etc. The molecular dynamics can be used for various purposes, like frequently used in tribology or surface chemistry, in energy applications. The next project is geometry optimization. This is the project supposed to find optimal relaxed structure for the system. It can be done with several calculations, includes several algorithms to minimize the energy. Let's go to the next slide. The next project type is equation of states, where a sub is running automated workflow to find equilibrium volume and the bulk modulus of the structure. It's all done automatically, so the project is running in automated way in the background and give you the output which related to the mechanical properties of the materials. The next project is nudge elastic band. This is the project related to definition of saddle point and finding the minimum energy path between reactant and products. This is the standard algorithm to use for catalysis applications, to finding transition points and reaction paths. There are several algorithms implemented in ASAP, so some of them are very accurate, some of them are with reduced accuracy to speed up the calculations. Next project is Phonon. This is to calculate, perform phonon analysis of periodic system. Similar project but related to non-periodic system is called vibrations. I think it's in the next, yeah, vibrations. This is the top one where we run vibrational modes for non-periodic systems. This is both of the projects are very applicable for IR techniques, for example, for experimental techniques, for neutral scattering, IR Raman spectroscopy, which allows to identify specific modes which experimentalists can see and see the changes with respect to the external conditions or the solvent, etc. So calculations allow to see this mode, to visualize them, perform the analysis of modes and the frequencies. The next project is optical response. Essentially, is to calculate absorption spectrum of a material as a real and imaginary part of the electric function. Next project is interaction energy. This is to calculate energy of the chemical reaction, essentially reaction energy, and it's also done in an automated way. The next project on the next slide is interfacial energy tool. This is again a workflow to understand how the energy is evolving of a molecule approaching the surface or two molecules approaching to each other. So this project includes several calculations and allows to fit the interaction energy with analytical functions. The outcome of this project can be used for molecular dynamic calculations performed with classical approximation. Essentially, this project can fit interatomic potentials for classical calculations. Right, the next two projects, convergence tools, are merged together. You see both of them. Essentially, for any ab initio calculations, the optimal set of parameters should be converged with regards to the energy. So normally in DFT codes, it can be done manually or with the scripts. In ASAP, this is done in an automated way with a workflow. And these two projects allow to find optimal mesh cutoff and Brilliant zone samplings with these with this tool. Right, I'm going to the next project, which is local density of states. This is the project devoted to calculation of molecular states or molecular orbitals and visualization them or saving them in the external file. This is a very useful tool for interpreting homolumous states, for example, states also for scanning tunnel microscopes. And in ASAP, we have 3 different ways to visualize these densities. You can save it in an external file, you can see it in a 2-dimensional projections with ISO lines, or you can see it in a 3D viewer in a semi-transparent way. Right. The next 2 projects are related to electronic nano-Transport. Essentially, these are the project which uses transistor code to calculate nano-Transport and characterize nanoelectric devices. So the projects are using siesta and transistor to see potential profile under the finite basis and voltage and currents. The outcome of the project gives IV curve, essentially current versus voltage curve for the nano device. It can calculate the conductance and give the properties of the transmission. Right, I'm going to the next slide. Federico, could you change the screen, please? So as soon as we define the project, we can run a calculator, in our case siesta or trans-siesta or teletrans. And siesta is ab initio code to perform a very efficient electronic structure calculations. Siesta allows excellent performance for periodic finite and open systems, especially is very efficient for open systems. The performance of siesta is much better in comparison with plane wave codes like VASP or Casper. This is because of the design of the code. We don't deal with plane waves, we're dealing with the localized basis set. On the top of that, the speed of the calculations can be tuned with regards to the accuracy of the basis set. There is a flexible way to change the accuracy basis set. That is why dealing of the systems over 10,000 atoms, it's a normal task for siesta. Siesta is very efficient for these tasks. Siesta, as a calculator, also has a very efficient linear scaling algorithm. This is for over tens of thousands of atoms calculations. And on the top of that, we will be showing later non-equilibrium electronic transport using trans-siesta. Right. In ASAP, the properties of DFT solver siesta are parameterized already with a very optimal and converged parameters. Essentially, non-experienced user can just open and ignore these parameters, and siesta will be running, giving a very decent results. For advanced users, of course, these parameters will be changed and tuned. For example, starting from physics, for example, changing the exchange correlation functional, or changing the parameters of the convergence, or the details of the basis set, etc. ASAP also allows to perform dipole correction or simulate doping or apply external electric field in different dimensions. ASAP also supplies the library of basis sets and pseudopotentials. So normally a user has to think about where to take pseudopotentials or what kind of basis set to set, while in ASAP this is already taken care of, and artificial intelligence already set all these parameters into the parameters of calculations. Let's go to the next slide. As soon as the solver is done, we go to the next step, which is run simulations. The run simulation widget, it looks as it's shown on the screen. Essentially, ASAP gives the output of siesta into the special windows, so the user can monitor the calculations, or if it doesn't interested in that, he can just close the window and the calculation goes on the background. The status of the calculation is written on the bottom by the green letters. It can be completed or running. so the user can see the status of the calculations. Let's go to the next slide. As soon as the calculation is completed, as it's written on the top part of the slide, you see the green letters completed. That means that the project is completed, calculations is converged, and the button Analyze is active. So depending on the project, the analysis widget can be different. For example, for single pole calculation, when the user asks for the density of states or band structure, he can see, for example, the picture on the left, it shows the electronic band structure and the density of states. Or, for example, for the optical calculations or vibrational calculations in the given spectrum, or for natural elastic band, you can see on the right side, you can see the profile between the red and blue. This is the reaction profile with the transition point of about 0.374 eV. So this is such the reaction between two mostly equivalent states. Right, let's go to the next slide. So as a summary, a sub is a cross-platform code which can operate under different flavors of Linux, Macintosh system, and Windows. A sub doesn't need installation, it goes together with installers and all the libraries together. A sub is a very flexible GUI which allows a full automation of your calculations. A sub supports local run as well as flexible control of remote machines. So a user can set up several remote clusters with flexible scripts and time control for remote calculations. ASAP provides automated convergence tools and all the parameters necessary for ab initio calculations. ASAP is using siesta and trans-siesta solvers, which are very powerful for the big systems, which are overpowering the standard plane wave codes like BASP and Custard. ASAP also has lots of advanced features like structure builder, 3D solver, 3D viewer, robust solver, and complete analysis widget. If you would like to use ASAP, please go through the link, which is written on the bottom, and request a trial version. We will be happy to supply it to you. So that will be all for this presentation. I'll give a word to Federico, Dr. Marquesin, who will give a demo of ASAP.
Okay. So let me share the other screen. So now you should see my other screen with the sub open from. Is that correct? Can you see?
Yes.
Fantastic. Okay, thank you. So Anna gave a quite comprehensive explanation of all the projects that can be done using ASAP and general features. So now the idea is to look more into the detail on how practically this is done with ASAP in order to have a real flavor of how a user can effectively interact with our code, with our software. So as Anna said, ASAP can run on Unix systems, so Linux and macOS, and also Windows. I'm currently running this on my Windows laptop. So I will show you how to basically to set up some calculation and run some of those. Obviously, these are just examples, so will be applied to a very small molecule or easy system. But you need to think that in practically this can be applied to any kind of the system that you like to calculate. So initially, this is as you open the first time the software, this is completely white because there is no project initialized. And as you'll see in a moment, in this white screen will be filled with the project that we'll be creating time by time. So the first things to do, as Anna said, is defining the system. So this is the first step, always. We have some ways to create, in a very fast and easy way, molecules. So this is by clicking this icon here, you have access to a series of database. each of them with some molecules, as you can see in here in my screen. I can also type, if I know the chemical formula of my molecule, and select the one I want to compute. In this case, I'm going to choose water. So if I press on OK, I will have now a new project created, as you see here. On the left, you have the image of your system, and then the different buttons that Anna explained previously. So this is how you create a molecule. This is one way in which you can create your system. Okay, we will see later how to visualize and edit your system. Now I'd like to go through the other buttons here on top in order to see how we can create the other kind of material. So we created basically a molecule, so a final system, and we can create a bulk. In this case, this is the widget. Okay. First thing is selecting the element, okay, the composition of your bulk system. You can do so by using this periodic table or just by typing here the element. So in this case, for example, let me choose copper. April lattice constant. In this case, ASAP will choose for you the lattice, and the user will have the possibility to select specific representation depending on the need, on the specific need. If I choose primitive cell, then there will be only one atom per cell, which will be duplicated in each direction XYZ in order to create an infinite system. I will show you this in a moment, and yeah. If I press on OK, then I have a new project newly created with a system that I just selected. Another very interesting feature is how to create a surface. This is usually painful because there are different kinds of surfaces, okay? And those surfaces are indicated by what's called Miller indices. And so there are several combinations of these Miller indices in order to have specific surface for any kind of crystalline structure. And with ASAP, this can be done in an automatic way. First, we need to choose the bulk. So this is the same widget that you just saw before. And for example, here, let's choose gold, FCC, primitive cell, and I press OK. So here I have my bulk. Then now I can cut. And I can decide along which direction I want to cut it by changing the Miller indices. And obviously, this is a surface, so I can, what we do is to choose the thick of the surface to effectively create a slab. This is done by changing the number of layers. And I can also extend this surface in plane. This is a primitive cell, but I can create a supercell and by basically changing these two values, so repeating plane, which, for example, like this. Let's choose 2, 2, and 4, for example. Last parameters here is vacuum. As I just said, this is what we are doing is effectively to create a slab, and it's important to add some vacuum for technical reasons that I will show you later. So if I press OK, then I created my surface just here. We can also create, going faster through these, nanotubes of carbon or silicon by choosing the chirality, the chiral indices, and also the linear extent of the system, as well as the vacuum, as in the previous case, and the bond length, so the distance between carbon atoms in this case. Finally, I can create cluster. this is the fifth option you can select through many elements of the periodic table, and the lattice constant and the number of shells. So by changing the number of shells, I change basically the size of this icosahedral cluster. When I'm happy with it, I can create it. Okay, if you are not happy with all the options that we already provided in ASAP, you can always import structures. So nowadays there are plenty of databases or just previous calculation from which you would like to import the structure. And this can also be done by using the function import. Many different files can be imported. Most common, cube, SIF, PDB, as well as some output file from other existing code as you see here, games, Gaussian, and Siesta. In this case, I've here already created, obviously, a PDB file format of this ROY molecule. And if I open it, well, I will have another project, as in the previous case, with the created structure. Okay, so I would like then to run a calculation, and then I will add some few words on how we can further edit and visualize the different structures. So imagine to take this first project, which is a small molecule, so I can run it in just a few seconds on my laptop. Okay. There are different projects that you can choose from. Anna went through all of them, so I'm not going to spend more words on it. I'll choose single point calculation, which is the most basic one, if you want. But it allows you to calculate some properties that can be selected in these windows. Specifically, those density of state, projected density of state, band structure, which in this case is disabled because it's a molecule, so this is meaningless, and ASAP knows that, and so it doesn't even give you the possibility of doing so. Charge, then you also battery analysis and electrostatic potential. In this case, let me choose just DOS PDOS and charge analysis. There are also other variables that the user can change, such as atom position, magnetic moment, and atomic masses. Well, magnetic moment is particularly important in case of magnetic systems. So, indeed, if you load a magnetic system as automatically recognized, so, but the user can always have complete freedom to add collinear and non-collinear spin calculation for magnetic system. Okay, I press OK. Then the next step, which can be skipped, because ASAP takes care anyway to set up all the some default parameters, is the step in which you define the parameters of your calculator. You can choose among different calculators. Okay, now there is this classical force field calculator, and then I have here Siesta and Transiesta. So in this case, I'm going to perform a Siesta calculation with Siesta 4.1 version. So you have some physical convergence, basis set and pseudo potential parameter that Anna already explained, so I'm not going through this, with some advanced parameter option in certain cases. So the user can play around quite a bit, but there are often, unless you don't want to do something very specific, normal user can just kind of forget of these parameters and use the default ones. Always for very expert user, it's always possible to visualize the input and to change whatever you want. Obviously, this need to be done carefully, because you can mess with your calculation. As long as you set up parameters through the GUI, we can ensure that there will be no conflict in the flag and the calculation will be carried out properly. but manually change the FDF can be dangerous. But we give the user this possibility. Then the next step is to effectively run my calculation. This can be done locally, even in Windows, because we have serial and MPI version of Siesta compiled for Windows, or on an external server, which you want to do for big system. In this case, I'm using a small molecule, a water molecule, so I just use the serial version of Siesta. And I just press on run. As you will see, this widget gives you also an update on the status of the calculation by basically showing you the output file. There is some delay here, but you should see soon. Well, wait a second.
It's your promotion.
Yeah, I have a lookup. I think it might be because I'm sharing the screen and this. It's a bit too much for this laptop.
You can close it and take it.
Yeah, let me do it again. Just to be. This. Yeah, I'll try on computer machine for this.
Okay, do you hear me? Sorry for this technical problem. I will now try to run on my machine. Okay, it was water molecule. And I'm going to the run widget. And just executing. Okay. And you can see now the output. So this is output from Siesta. We can see that it performs self-consistent field iterations and converges density matrix and Hamiltonian. And it writes forces and so on. And finally, the calculation is finished. Now I can go to, I can press the button exit and analyze. And then I can see the analysis widget. Okay, so here I can see the input FDF file, the output file again, eigenstates, eigenvalues, HOMO, LUMO, gap, and density of states. I can adjust, I can change the type of smearing, for example. Well, it doesn't, this molecule is not very important. Minimum, maximum, widths, for example, I will set it to like this. Okay, maybe I want to see. Okay, so I can adjust it as I want. I can put Fermi Ehrenfeld 0 and so on. What next we are going to discuss?
Well,
You can show the some of the atoms are inactive. How to activate
So yes, this in the output, some of the properties are inactive because we didn't set to calculate these properties. What we can do is to go to the parameters widget, to properties, as Federico showed, select electronic dose, P dose. I didn't do it in my calculation. Charge, okay. Yes. Then I redo the calculation, which is very fast. And okay, now in the analyze widget, we can see P dose, for example. Here we can select the orbitals that we want to see, like species. We just want oxygen and only p orbitals. Okay, only p orbitals. So we can say add curve. So we can now we can see another curve which is only for oxygen and for p orbitals and the whole dose. And charge. Okay, in charge we can see partial charges on the atoms for using Mulliken, Hirschfeld, and Voronoi schemes. So for oxygen, hydrogen, and we can export it to text file.
I'm going to show the
Edit structure.
edit structure and merging structures.
on here?
Well, I can do it on every shape if you want.
Okay, please.
Sorry, I had a problem with Microsoft Teams, who does not allow me to log in again. So, yeah. So I changed PC. This is Linux indeed. So what I was going to show you next was how to merge existing structures. So in my case previously, if you my PC, if you remember, I created, and I'm doing it again, a surface like this, for example, within a vacuum. Okay, so I have these two projects already initialized. One of those can be already completed, but this is not necessary. What I can do next is to merge these two structures by selecting them. Yeah, and this can be useful, but this can be done. I mean, in this case, I use a molecule and a surface. This application, this is, for example, for catalytic application, in which you have, for example, association or dissociation of certain given molecules or gas on a surface. But can be done also by putting together two different surfaces. If you want to, for example, study how two surfaces can interact with each other and merge it together. Yeah, this is the widget. I'm not going to go through these parameters related to constraint, but basically you can decide which atom you want to fix or not, depending on the kind of calculation that you want to do next. So in this case, for example, another parameter that you can set up is the distance between the two systems. And here, well, this is just a visualization angle, so you can decide. It's just a change of visualization. So when I'm happy with it, I can press OK, and I have a new project with these two systems together. But this is not the end. I can always open, using this widget, my system and inspect this system. So I can just visualize it. Okay. I can even repeat the cell to see how the periodic system, the surface, will look like. So in this case, I have a matrix of water molecule on top of a gauze surface. So this is for visualization purposes, but I can also effectively modify the structure. So if I select the surface, the molecules, and Control M in order to move the molecule, I can select the specific position in which I want to put the molecule on my surface, and also the distance from the surface. I can change it. Other action that can be done is a molecule rotation. So I can rotate my molecules. So in this case, I can put the oxygen pointing towards the surface. And when I close the widget, ASAP is asking me if I want to save or not what I just did, the modification I did. If I press save, the project is updated with the new system. Another things that can be done in terms of editing is editing the cell. This is particularly is useful for periodic systems. One, not only so this, even in this case, the user needs to know what he wants to do, but there is in principle complete freedom to change not only the atom position as I just showed you before, but also the cell. For example, I can remove periodicity, add some vacuum, and the surface now becomes a molecule in vacuum, a weird system in vacuum. In this case, I'm not interested to this specific system. So when I close this widget, I say to ASAP, discard the changes, and I'm still as before with this surface with the molecule on top. Before we were mentioning that calculation can be run locally or on a remote cluster. This is a very important and powerful feature of ASAP, because this the user can completely forget about the usual pain of connecting through a cluster using the terminal, and always through a cluster perform the calculation. ASAP will take care of sending the calculation, monitor the status of the calculation, and retrieve the results that are important. Obviously, the user will always have access to the cluster, and so all the results will remain there. Nothing is lost. But ASAP will take care of copying locally those files that are important for the analysis for the specific project that has been chosen. So, for example, in this case, you will see this is what we call configuration runners. So this is where we configure the Siesta local and remote configurations. So in local configurations are basically the Siesta and Trans-Siesta and TB-Trans executable that are going to be run locally on the machine in which you are running ASAP. And then there are others, which are these ones, that are this is to run on a remote cluster. So, for example, if I can open this, no?
Yes.
So this is a procedure that needs to be done, obviously, but needs to be done only once. Once you set up this, the first time you open ASAP, basically, then you can forget, and I will show you in a minute why. So you need to, as in any SSH connection. You need to set up your host name, username, and you need to tell also where on the remote cluster is the executable, in this case, Transiesta. But once you've done so, then you're good to go. So basically, anytime I create a new project, for example, this random molecule, I go to run, and I can choose among, well, I don't have Transiesta now because I didn't select Transiesta project, but I can choose among the Siesta, in this case, 4.1 executable. These are on the local machine, and there is written here clearly, and these are on the remote cluster. So if I select, for example, this one, which is on our private cluster, and I press connect, then ASAP will take care of enabling an SSH connection to the cluster. And if I press run, then the calculation will be run on the specific cluster. I can choose the number of MPI processors. So running on big cluster is very important, because if you can use more than 100 CPUs, then you are effectively enabling calculation with hundreds or even thousands of atoms. These I'm running directly on my cluster, but I can also use what's called, do we have one with a queue system?
I don't remember which one.
Okay, but I show you here. Okay, this doesn't allow me because I'm just there. Okay, there is also the possibility.
This one. Okay.
But I'm not going to change anything.
Try to close and do it, because this one needs another.
Okay. So yeah, I was not going to change anything. So for example, there is also the possibility, okay, to run using a queue system. So basically, we support Slurm, PBS, and IBM LSF as a run management system. But the user can also have the freedom to use his own script, because we understand that some cluster, although using some well-known batch scheduler vendor as Slurm, still needs some further tuning in order to be properly used. So in this case, you can run your calculation on a remote cluster using a queue system, which will take care of submitting the calculation, monitor the calculation, and retrieve the results whenever this is completed. I think I've talked enough, but please, if you have any specific question of any of the project that you see in the previous presentation and you would like to know more, just let me know. Okay.
I'm presenting.
You muted?
No.
Okay. So the next topic in this webinar, it will be discussing the new feature developed in ASAP, which is related to electronic nano-transport with Transiesta facility. So Irina, Dr. Lebedeva, will be presenting these functions of ASAP. And after this presentation, we'll give you a little demo. How does it work?
To see if I'm presenting.
You're not presenting.
I'm not presenting. Okay.
Let us share the screen.
Okay.
Yes. Okay. Yeah, it's fine.
Okay. Okay. So we'll be talking about electronic transport. As you know, the current trend in electronic devices is to decrease their size. Every time they're getting much more and more smaller, and this means that we need to take into account quantum effects like tunneling current. In the case when the insulating layer of a transistor becomes small, there is leakage current that is needed to be taken into account. And quantum confinement, so when the active layer becomes thin, then there is quantization of states and properties. And to properly model these effects, we need to use a quantum approach. And such an approach is provided within non-equilibrium green function formalism. In the case of transiesta, green functions are constructed from density functional theory Hamiltonian, and we compute the current. So to compute the current, we use a Landauer formula in which we consider the states that are occupied for example, for left electrode and are free for right electrode. And in this window of states occupied in one electrode and free in the other one, we integrate the transmission function, which characterizes the probability for an electron with a given energy to pass from one electrode to another. And this transmission energy is computed based on the green functions of the electrode and coupling between them. So this formalism can be applied for a variety of systems. For example, it can be used to describe nano devices like modern transistors with hybrid geometries, like, for example, here's an example of combining graphene with carbon nanotubes, conductive inks, performance of devices in the presence of defects or quantum dots. Also, it is important for accurate description of reactions that take place when there is a voltage applied, for example, for corrosion processes. And it can be used for modeling for molecular electronics and modern sensors based, for example, on biological molecules like DNA. And recently we have implemented non-equilibrium green electronic transport in ASAP. Using the transiesta as the calculator. So what ASAP allows is provides automatic workflow that allows building the nano device. So taking two electrodes and merging them together, putting some contact in between, then relaxation of nano device geometry, computation of electronic transport properties within the formulas that I discussed before, and post-processing analysis of IV curves, transmission, etc. And so I will now discuss how this is implemented in ASAP. So first I will discuss automatic construction of systems with electrodes and scattering region. Then calculations with transiesta, considering zero and non-zero bias, and analysis of transmission function. So as for building the device, so in ASAP it's very automated, so you can choose what the structure that you want for electrode, for contact, and for the second electrode. The merger checks that the geometries of these parts are compatible, so that the cross-section is the same. Then you can change the orientation of electrode or molecule. You can, in transiesta, in this formalism, it's important that the system can be divided into parts along the transport direction, that these parts only interact with the neighboring part. For example, the first electrode part, bulk electrode part, interacts only with the contact, doesn't interact with the second electrode. And in order to achieve this, and also to be able to add some surface layers to the electrodes that needed to be relaxed, you can extend the electrode into the contact, and you can also add some buffer layers that can be used to put some extra charge that is appears in the calculation and to help charge conversion. So you can manipulate the geometry of your system here to make it thicker or longer, and you can adjust the gaps between the electrode and the contact molecule. It will also warn you if the system that you constructed doesn't allow you to get physically meaningful results. So the unit cell of the electrode is too small. it needs to be long enough so that the non-adjacent unit cells of the electrode do not interact with each other. So so the merger tool provides a easy interface to deal with these issues. So once the device is prepared, transport project is created, and it can be used for, it performs a series of calculations. So normally when you do by yourself using Transiesta as a calculation, you need to perform a series of calculations for electrodes, then you need for different voltages, you need to prepare the input FDF files for each of the steps to transfer the files from one calculation to another. So here ASAP takes care of all of it within this transport project. So first in the settings widget, you need to set, you can still adjust the geometry of your device. If later you see that it doesn't give what you expected, maybe it doesn't converge well, you can readjust some geometrical parameters here, and you specify the voltages you want to consider. And then, oh, sorry, back. So once you perform the calculation of transport properties using Transiesta, it is needed to perform analysis using TB-Trans utility. So this is another solver which is declared as TB-Trans, and we create a transport post-processing project. And this project, we can again readjust the voltages we want to consider, because we can perform interpolation of Transiesta results for different voltages. And then we can specify the energy grid and other parameters that are needed for visualization of transmission. And finally, from this transport processing project, we get the final results. We can, in the analysis widget, we can plot IV curve and transmission. It can be plotted for different voltages, for spins, if we did spin polarized calculation. And we can also compare how transmission compares with transmission of pure electrode, of bulk electrode. So now I will show you how this works in ASAP. So as Federica said, before doing any transport calculations, we need to be sure that we have executable, that we have declared Transiesta and TB-Trans executables in the way that Federica showed. And we need these executables to be compiled with NetCDF library, which is needed for a proper output. Then the first step in our calculations is to create electrode and contact structures. So in order to create an electrode, I open a create surface tool, as Federica showed before. And again, I can select, for example, select gold bulk, and select the Miller indexes for the surface, the number of layers. Normally, the unit cell should not be very short. And in this case, I just say, I want to use bulk simulation cell instead of the vacuum. Then the structure will be periodic in transport direction, but the interface will have the surface that we want. So now I create this gold electrode. I will also show you how to create a 1D electrode, like sodium chain. So I will set here sodium and simple cubic, and I will use just 2 atoms, which is enough. Okay, but now I need to manipulate the unit cell. I press edit structure, edit cell, and I increase the size of the unit cell in the cross section. I set it to 10 line magnitudes. I do it non-periodic and center. Okay. Now I have ready my 1D structure of sodium chain. Save. And now ASAP informs me that the K-point sapling has been changed to 1 and 1 in the cross section. Okay. Now I have a sodium chain, and also I can select a molecule as a contact. For example, ethylene. Okay. Now I want to prepare the device, and I select a few structures, electrodes and contact structure. And in the menu, I press to merge for transport calculations. Then merger tool is open. In this case, the first structure that I selected was gold. So it prepares the device from gold. But now I want to use sodium chain as an electrode. So I put here sodium chain for the first electrode. Automatically, it changes the second electrode also to sodium chain because it is the periodicity of gold and sodium are different. So it selects only structures that fit to each other. And for the contact, I select ethylene. Okay, and now I reset the gap. Okay, and here, for example, I can adjust the number of electrode unit cells in the buffer. Here I would put just one atom in the buffer. It's enough. Okay, update atomic structure. So now the structure, so I have now one atom in the buffer, 2 atoms in bulk electrode, and 2 atoms in the contact structure for each electrode. Okay, now it gives me the warning that I cannot, the lengths of the electrodes are not checked. In order to check them right here, I would have needed to perform previously the calculations for electrode, but I didn't do that. Well, it doesn't matter too much. Okay, I create now the device. It is this. So this is this chain with. So these are 2 electrodes with molecule in between. This is transport project. In the parameters, I can still adjust the number of layers in the buffer and in the contact, and I can put the voltages I want. I will let the voltages 0.1 and 0.2. Okay. Okay. Now I can also adjust some parameters, calculate the parameters for transistor. Just to make the calculations fast, I will put rough mesh cutoff, and also I will decrease the mixing parameter for the device. Okay, you can also here for transistor, you can also adjust additional parameters like whether you want to use charge correction, it helps convergence, and also whether you want to adjust the integration contours. Okay. Now I go to the run widget and I will run it in my machine because it's small. Okay. Now it's starting to run. So it's running a series of calculations actually. So the first what it does, it checks that the length of the bulk electrode units and contact lengths are long enough so that calculation gives physically meaningful results. Then it performs calculations for each electrode. Well, in this case, second electrode is the same one as the first electrode, so the results for the first electrode are just copied. And now it performs a calculation for the whole device. So first it performs standard siesta calculation for the first device to converge the density, the equilibrium density. And now it performs the calculation already for 0 voltage. Here, it gives some output on how the charge is distributed on different parts of the device. And what we need to look for is that density, how density matrix, Hamiltonian are convergent, and also the charge, excess charge that is not associated with any part of the system, that it also needs to be very small. Okay, now it's doing the iteration. They take some time because transport calculations are heavier than standard siesta calculations. Even for this system, it takes more time, but okay, we already have results for 0 voltage. And now it's doing for voltage 0.1. Okay. We can also here preview input. If you look in the input FDF file, you can see that ASAP has added this, all these input parameters for transistor. So it's description of the electrodes, where the results for electrodes are, how to perform integration. So all this that you can change through the GUI is here in the input file. But of course, it's much easier to put the parameters in the GUI which have descriptions than to construct this very long input file for transistor. Okay, so now the results are ready. This is transistor run, and what I obtained from it is just the files, the Hamiltonian overlap matrices for different voltages. And now, in order to analyze them, we create transport post-processing project by just clicking the button. And it created this transport post-processing project. And here the system is already set. We just can add some more voltages if we want. Add value. this will be very easy. We will just be interpolating trans-siesta results. It will not have much additional computational cost. And we can adjust the number of K points in the cross section if needed, and energy grid. Well, here the number of K points is not adjusted because it's just a one-dimensional structure. Okay. And now we perform the run also on the local machine, but this one will be very fast. Okay. So exit and analyze. And here we have the plots for transmission and current. So for transmission, uncheck current, we can see transmission. For this is 0 bytes transmission. We can add for different voltages and compare how they changed. And we can also compare with how bulk electrode transmission is. So it's on the right axis. So we can see that transmission for the whole device, this is from 1 to 2, is within this transmission of bulk electrons. This means that results make sense. So there is no any strange peak when there is no bulk electrode transmission. And then we can also see the IV curve. So it shows that how the current changes depending on the voltage. And then here, are you going to do the presentation?
Right. So, right, for this case, the transmission for this toy system, indeed, the current is almost linear, but for the system like you can stop sharing and I can share two top screens. Right. So let me share my screen where I can do that.
Okay.
Do I share?
Yes.
Okay. Okay. Right. So we can see another case study which I prepared for a bit more sophisticated system. Essentially, this system will be gold electrodes with the cysteine molecule as a contact. So essentially, I will not going to repeat all the steps which Irina has already described, but essentially the steps are the same. We create two systems, which is we have biomolecule sitting between gold contacts. So the transmission in this system is very important for biological applications, and this is the big area of research now. So I'm using a really small molecule of biomolecular system, but Siesta is powerful enough so we can put a really large molecule, large protein, and the transmission of this protein is really important for biological applications. And with Siesta and trans-Siesta, we can really see a real insight what is going on in the system. So nevertheless, let's going back. So I have a small biological molecule, cysteine, placed between two gold electrodes. Essentially, I'm following the same steps, merging two structures for the transport calculations. I'm setting parameters like buffer, contact region, which has been already explained. I use a little bit larger system. It's not just one-dimensional sodium chain, but essentially this is a 3x3 cross-section, which is a bit larger, and this is more close to the real systems. So Irina also mentioned that the distance between the contact and the electrodes, which is called gap between here, can be relaxed. There is a special project for this. I'm not going to do that in this particular example because the distances are more or less okay. Right. So at the end, we have this device, which is electrode, gold electrodes, and the molecule in between, which is correspond to this schematic picture on the top. So we start our calculations with, okay, right. This is we setting the parameters. Again, doing several voltages. Set the parameters for convergence, for contours, and then we run calculations. So as Irina said, this workflow is really automated, so the user doesn't really take care what exactly has to be done. But essentially, there are several calculations done one by one, inheriting the density matrix, using them as the initial guess, and converging the electronic structure. So here we have seven calculations for different voltages, including 0, 1, and I'm running these calculations on parallel machine with 32 processors because the system is a bit heavier. The Siesta shows the input, the output, which is welcome to Siesta. And when the calculation is done, the project has marked as completed. So if you press analyze, it shows that this sequence of files has been created. These are raw files used by TB-Trans for post-analysis. So ASAP invites you to create another transport post-processing project. And if you click on this button, a new project, transport post-processing, is created. So in that case, as Irina said, we can add several values here, but these values will be just interpolation, but not a real calculation, so it will be much cheaper. Right. This is post-processing, and this is the final result. So the project is completed as marked here. So what we have here, so essentially the standard output widget shows two graphs. One is the transmission, another is current. So not to mix up both things, let's consider transmission first because there is plenty of information on this widget. So for example, we can choose voltages from negative to positive, and we see how the transmission function changes. We can see indeed the changes from blue to purple. So there is a shift, which is a physical meaning of this. So we can also compare how the transmission function changes with the presence of molecule between electrodes, because we can draw the bulk, the lines for the bulk. In that case, it will be these broken lines, and the solid lines is related to the molecule. The values for transmission for the molecule is written on the left, and for the electrodes are written on the right, so the scales are different, you see. So essentially, molecules are almost 10 times smaller, right? So if you click on the current, we can see another window. And here, what we see here is that indeed the IV curve, essentially current versus voltage curve, is not linear anymore as in the toy model, but indeed shows a bit different properties. This is what really is seen in experiment, and this is really interesting. For example, for 0 voltage, we have 0 current, but as soon as we change it, there is an increase of the current, but there is also a drop. So this is antisymmetric curve, and these results can be directly interpreted by the experimentalists. Right. So as a conclusion, since I see 5 minutes left in our meeting, so what we can say, the transport properties is a new feature in ASAP. And this is a very flexible workflow and allows a very nice device builder and visualizer. The transport properties can be calculated as an automated workflow with including geometry relaxation, with full control of parameters of calculations, including advanced features like integration contours, etc. If you would like to use or try this feature, please send us a request for ASAP on this link at the bottom or visiting our webpage. Right, so if you have any questions, we are happy to answer. Right, no questions.